In 1960, a physicist named Freeman Dyson published a scientific paper in the journal Science with a modest title: Search for Artificial Stellar Sources of Infrared Radiation. The paper was 3 paragraphs long. It did not include a single equation. It was, in terms of sheer page count, one of the least substantial contributions to the journal's history. It also contained one of the most consequential ideas in the history of speculative science. Dyson's argument was simple. Any civilization advanced enough to survive its own technological development would, over sufficient time, exhaust the energy resources of its home planet. The logical response for a species with the technical capacity would be to capture the energy output of its star. And the most efficient way to do that, at the largest possible scale, would be to build a structure that surrounds the star completely, a shell, a swarm, or a ring that intercepts stellar energy before it radiates into empty space. This concept, now called the Dyson sphere, has been a fixture of theoretical physics, futurism, and science fiction ever since. But in the last 2 decades, it has migrated from thought experiment territory into serious engineering analysis. Researchers at universities and national laboratories are now examining the actual physics, materials science, and orbital mechanics of megastructures. The question is no longer purely, could a civilization eventually do this, but what would it actually take? The answers are remarkable. First, some numbers that establish the scale of what we're talking about. The sun outputs approximately 3.8 times 10 to the power of 26 watts of energy continuously. This is the total electromagnetic radiation, light, heat, ultraviolet, infrared, emitted in all directions from the surface of a star that has been burning for 4.5 billion years and has enough fuel to burn for roughly 5 billion more. Earth, at a distance of approximately 150 million kilometers, intercepts only a tiny fraction of this output, roughly 1 part in 2 billion. This intercepted fraction represents approximately 1.7 times 10 to the power of 17 watts. Humanity's current total energy consumption is roughly 2 times 10 to the power of 13 watts. In other words, the sunlight falling on Earth alone, if perfectly captured, would supply humanity's current energy needs roughly 10,000 times over. Now extrapolate to a structure that captures the sun's entire output. A perfect Dyson sphere would intercept 3.8 times 10 to the power of 26 watts, roughly 10 trillion times humanity's current energy consumption. This is not a modest upgrade. It is an energy budget so vast that even the most extravagant conceivable uses of energy, terraforming planets, powering interstellar probes, running computational systems of unimaginable scale, would barely register against the total. This is what is at stake. Not a better power grid, a fundamentally different category of civilization. The original Dyson proposal was deliberately vague about the physical form of the structure, but popular culture latched onto the image of a rigid shell completely enclosing the sun. This image is technically the most problematic version of the idea. A rigid solid shell faces immediate and catastrophic physics problems. A shell at Earth's orbital distance would need a radius of approximately 1 astronomical unit, 150 million kilometers. At this radius, any rigid shell would experience enormous tidal forces. More fundamentally, a shell in the gravitational field of a star is unstable. Any slight off-center displacement creates a gravitational imbalance that accelerates the shell toward one side, causing it to eventually collide with the star. There is no restoring force that would return a rigid shell to its center position. It would require continuous active correction, thrusters, adjustments, perpetual maintenance at a scale that would itself consume significant energy. The mass requirements are equally daunting. Even a shell just 10 centimeters thick, made of something as light as aluminum, at Earth's orbital radius, would require a mass of material approximately 8,000 times greater than the mass of Earth. We would need to disassemble every planet in the solar system, including gas giants, and still fall short. This is why serious engineering proposals for megastructures have moved away from the solid shell concept and toward the Dyson swarm. A Dyson swarm is not a single structure, but a vast collection of individual, independent units, satellites, collectors, power stations, placed in orbits that collectively intercept a large fraction of the sun's output. Each unit is individually self-stabilizing in orbit. The swarm can be built incrementally, starting small and expanding over time as construction capacity grows. It does not require exotic materials. The basic units can be built from conventional materials in principle. And unlike a solid shell, a swarm does not create any impossible physics problems. The path to a functional Dyson swarm, as analyzed by physicists and engineers, including Anders Sandberg of the Future of Humanity Institute, begins with a bootstrapping problem. To build megastructure components at the scale required, you need industrial capacity that doesn't currently exist, and building that industrial capacity requires energy that a nascent megastructure program can't yet supply. The proposed solution is to begin with a small seed, a collection of solar collectors near the sun, perhaps in the orbit of Mercury, where solar flux is much more intense than at Earth. This initial installation generates power that drives automated mining and manufacturing operations on Mercury or asteroids. The manufacturing system produces more solar collectors, which are placed in orbit, which generate more power, which support more manufacturing, in an exponentially growing loop. This kind of exponential self-replication is not science fiction. It is in principle achievable with technologies that are extensions of what we already have: robotic manufacturing, autonomous systems, photovoltaic cells, mass drivers to launch material into orbit without rockets. The mathematics of how long this process would take, starting from a small seed installation and doubling capacity at reasonable intervals, suggests that a civilization could reach full stellar coverage in timescales on the order of thousands to tens of thousands of years. Long by human standards, brief by civilizational ones. The thermal implications of a Dyson sphere or swarm are what make it detectable from a distance. And this is where the concept connects to the search for extraterrestrial intelligence. A structure that captures stellar energy would absorb it, use it for whatever purposes the civilization requires, and then radiate the waste heat. By the laws of thermodynamics, even perfectly efficient systems must emit waste heat. A Dyson sphere radiating the waste heat of a captured star would glow in the infrared spectrum at a temperature determined by the distance and surface area of the structure. For a structure at Earth's orbital radius, the predicted waste heat temperature would be around 300 Kelvin, roughly room temperature. This would appear as an anomalous infrared source where a star should be producing visible light. The star would seem dimmer than expected at visible wavelengths and anomalously bright in the infrared. Several searches of astronomical databases have been conducted looking for exactly this signature. In 2015, a star cataloged as KIC 846238852, quickly nicknamed Tabby's star after citizen scientist Tabitha Boyajian, who first drew attention to it, was found to exhibit unusual dimming patterns. The star dimmed asymmetrically, with varying depths and durations, in patterns inconsistent with conventional explanations like planetary transits. For a brief, exciting period, some researchers seriously proposed that partial megastructure construction could explain the data. The consensus among astronomers has since settled on explanations involving dust clouds, though the debate about Tabby's star is not entirely closed. The episode demonstrated usefully that the question of megastructure detection is now taken seriously as an empirical matter, not as philosophy, but as astronomy. The construction of a Dyson sphere, or any megastructure that captures stellar energy, would represent the crossing of a threshold. It would mark the moment a civilization's energy budget became effectively unlimited, not as hyperbole, but as a meaningful physical statement. A civilization with access to the full output of its star has energy available on a scale that makes everything we currently consider energy-intensive trivially cheap. Interstellar communication, artificial gravity, computation at scales that would allow the modeling of entire planetary ecosystems in real time. The acceleration of probes to significant fractions of the speed of light. The Kardashev scale, proposed by Soviet astrophysicist Nikolai Kardashev in 1964, classifies civilizations by their energy consumption. A Type 1 civilization uses all available energy on its home planet. A Type 2 civilization uses all available energy of its home star. A Type 3 civilization uses all available energy of its home galaxy. Humanity is currently somewhere between Type 0 and Type 1. The Dyson sphere is the engineering project that gets you to Type 2. Freeman Dyson wrote 3 paragraphs. He was describing, in the most compact form possible, the next step in what a civilization becomes. Whether we build it is an engineering question. Whether we try may be the most important strategic question our species will ever face.